Ready? Okay, great. So let's dive in. So okay, this one's it's a little nicer in terms of the setup here. I mean, often when we're talking about the knapsack problem, it's within the context of us being a burglar and we're trying to steal stuff from somebody's house and we're trying to get away with as much value as we can within a certain weight capacity is the idea. So this is kind of modeled after that classic problem, except in this case, they're saying we found two items in a treasure chest. So it starts out a little more innocently, which is nice. Okay, and so basically the idea is that the first item, it has a weight that they give us, it's weight 1. It has a value they also give us, it's value 1. The second item, you guessed it, it has a weight of weight 2 and a value of value 2. And our capacity, you know, the capacity of our backpack or whatever we're using to travel with, it has a capacity of maxW. So that's the maximum possible total combined weight that we can carry here. And we can't come back for later. We can only take one of each type of item at most. And we can take both, we can take one of them, or we could take none of them, is basically the idea. And that's kind of what we're trying to sort out here. So again, if we want to look at this in the most naive, straightforward, word for word kind of interpretation, then we would say something like this. You know, if the maximum weight would accommodate both of these. So if we can take both of them, weight 1 and weight 2, great. Let's do it. So, whoops, that was not meant to be a plus. It was meant to be a closed parentheses. So in that case, we'll just return value 1 plus value 2. I mean, that's what we're looking at here. We're adding both of the values. We can get them both. Let's get them both. Now, if we can't do that, then we're going to do something else. And so at this point, you know, I might be tempted to do like an else or something like that. But the reason I'm not going to do an else is because it's kind of implied since there's a return here. The return is going to end the function. So, you know, if this ends up being true, if we do get to the return statement here, then that's it. We're not going any further than that. So we don't need an else because it's not going to get to whatever's below here if it ends up being true. So it's kind of like a natural else in that sense. So basically what we want to say is, well, if you can't take them both, then probably try to take the more valuable one. And if you can't take that, get the less valuable one. And if you can take that, take nothing. But the point is, we need to sort of figure out which one's the more valuable one. So we'll say, well, if value 1 is greater than value 2, then we'll do something, right? This will be the world of where the first item has a greater value. And in the scenario where the second item has a greater value, we'll do something else. So basically, what are we going to do? Well, we'll say, can you accommodate the first item? Since we know it's the more valuable one, it's the one we should really be going for. And we know, since we made it here and we didn't get caught on this, we know that we can't accommodate both items. So since we can only at most accommodate one of them, then we want to say, well, could it be the first one, since the first one's more valuable in that case? And if so, return the first value because you can get it. Otherwise, we'll say, well, okay, in that case, is it greater than the other one? Because if it is, then yeah, return value 2. And if neither of those, we'll just return 0 because that means we really can't accommodate any of these. Okay, and then basically the other case is going to be really similar. We're just going to say, well, in that case, if we made it to the else, that means actually item 2 is more valuable, so we'll prioritize that. And if we can get weight 2 and if we can get object 2, basically if we can accommodate its weight, we'll take it. If we can't, then we'll try to take the other one, and if we can't get that one, we'll return 0. So same sort of thing as what we had above there. Let's run this and we'll see what happens. Okay, great. Now there are other ways we could do this. You know, like for example, we could say if value 1 is less than value 2, then we'll switch them. We'll just say like value 1 and value 2 will be assigned the value of value 2, value 1. This is a really cool way of switching the values of two variables in JavaScript when we don't want to have to use like a temporary variable in the middle, which is really nice because, you know, it used to be that you always had to do that. You always had to have like an intermediate kind of variable, like a temp or something like that in order to switch these up. But I think this is called destructuring assignment or something like that. Anyway, point is, we'll say, all right, well, if value 1 is the lesser value, then we'll switch these. Otherwise, we won't switch them. So because of this, we know that value 1 will be, or object 1 will have the greater value. So let's just do the thing that we normally would have done if that was the case. And that way, we don't have quite as many return statements to worry about. We're basically just saying, switch them if you gotta, and then try to take the, okay, I'll put this in the comments. So switch the items if the second one is more valuable. So it's kind of like sorting an array, except the array happens to only have 2 items. That's sort of the idea here. And then what we want to say is, if you can carry the more valuable item, do it. And if you can't, if not, try the less valuable item. And if you can't carry either, you get nothing, which is 0. Okay, so we'll return 0 in that case. And I guess I should probably also mention, take both if you can, right? That's sort of what we're doing originally. That's kind of the philosophy behind that first line there. So great, this is nice. It's very descriptive. We're explaining to the reader exactly what we're doing. We're going to try submitting this. And great, it passes all the hidden tests. So that's nice. Making our way through the dark wilderness. But I did mention before, this is a pretty classic dynamic programming example. So the reason they're calling it knapsackLight and not just, the knapsack problem, is because we're constraining this to just 2 items. In the generalized knapsack problem, we could have arbitrarily many items. It might be 2, it might be 10, it might be 1,000. The point is, it would be cool if we could make an algorithm that would work for any number of items, right? So not just knapsackLight, but knapsackHeavy. We want basically the real version, the real deal algorithm. Because, that would be nice, right? I mean, knapsackLight, it's kind of like we've got the kid gloves on, Not to say that this is an easy challenge or anything like that, but just I want them to give me some credit, right? To believe that I can actually handle the full version of this. So in order to prove that, let's make an algorithm that will accommodate the full version. So in order to do that, let's just say, let values be assigned the value of an array containing value 1 and value 2. And we're going to say let weights be assigned the value of an array containing weight 1 and weight 2. Okay, no surprises there, I don't think. And we're going to say let dynamic programming be this empty array. And as it turns out, it's actually going to be, ultimately, it's going to be an array of arrays. It's going to be kind of like a big old matrix. Now, what is that matrix going to represent? Well, okay. DP here stands for dynamic programming. That is the main thing to keep in mind. We are doing dynamic programming. Now, if you did not watch the Task 33 video, I would recommend it. It's a really nice intro to dynamic, to learn what it's all about, when we want to use it, but just to sort of give you the Sparks notes on that, the idea is that dynamic programming is kind of like a way of breaking down a large problem into a bunch of overlapping sub-problems. Now, when I say sub-problems, I basically mean just like, taking smaller pieces, breaking it down, sort of like a divide and conquer strategy. But the main thing is the way we're going to conquer this is by addressing the fact that the subproblems are going to be overlapping. So there may be like some values that we've already calculated, and instead of recalculating those values, the philosophy behind dynamic programming is that, well, we don't. Instead of recalculating anything, we just keep track of all of our calculations. So we'll basically have a big matrix representing all of the calculations we've done so that we don't have to redo any of them. So again, let me know if you have any questions about any of that. I realize that probably seems kind of abstract at this point. So maybe what we'll do is we'll dive into this. We'll give it a shot. We'll try to see how this whole thing's working. And if you're finding, I don't know about this, it's still kind of giving me some problems, then in that case, I would probably recommend taking a look at the Task 33 video, because I think it's a pretty good intro to dynamic programming. If you're still having troubles, like, I mean, look, there's lots of resources online, lots of dynamic programming problems available. You know, search Google, you'll find lots of them. And, you know, probably you'll find resources from people who could explain it a lot better than I can. But anyway, we're going to try it. We're going to give this one a try. So we'll say something like, well, okay, let's come up with a game plan, first of all. So when we're talking about these overlapping subproblems, what do we really mean? Okay, so first, let me get a nice color for us to talk about this. Yeah, I think that'll be a good one, kind of a dusty rose. So we're going to make a matrix. Matrix being sort of like an array of arrays, and it's going to be kind of arbitrarily large. It's going to depend on our values here. And again, we want to be designing our algorithm in such a way that this will work for 2 items, it'll work for 1,000 items. That's kind of the idea. Okay, so on this axis over here, like what the columns are going to represent is our weight limit. Okay, so weight limit, I probably should have just written limit. That would have been a lot faster, but oh well. Our weight limit. Okay, so first we're going to say, all right, well, what if your weight limit's 0? You can't carry anything. What if it's 1? What if it's 2? What if it's 3? ... all the way up to maxW. And that's the thing that we're really interested in, is what's going to happen at maxW. But in order to make it easier for us to calculate that value, we're going to calculate all the values that come before it. Which again, probably seems like a really weird thing to do. It's like, why are you doing all those calculations if you're only looking for this last one over here? And yeah, I realize that. It does seem kind of strange, but this scales up really nicely. That's the thing about dynamic programming. It often seems like magic, and it does an amazing job at sort of, I was going to say the higher levels, but I don't want you getting the wrong idea. What I just mean is like for very, very large values, like if you had 1,000 different objects in this case. Okay, so this here is going to be a little bit different. So this is going to be kind of like, which items are we using? And we're going to introduce them one at a time. So for the first row, we're actually going to say none of them. This is going to be for no items. The 0th row, I should say, not the first row. For the first row, row 1, we're just going to have item 0 in here. For the next one, we're going to have 0 and 1. So it's kind of like we're doing this one step at a time. We're going to say, all right, well, if you have no items and your weight limit is 0, well, you're not really going to be able to get anything out of this. In fact, if you have no items, you're just not going to get anything. So we're just going to have zeros for the entire first row. But then after that, we're going to say, okay, well, if we only have item 0, like, or, you know, the first item, I guess, in this case it's called, well, it doesn't have a name, but we could call it item 1, the thing that's going to have weight 1 and value 1. Okay, so for this one, let's take a look at this example, actually. So weight 1 is 5, value, that's value 2. Whoops, okay, sorry about that. Weight 1 is 5 and value 1 is 10. So basically the idea is we'll say, okay, we're just looking at that one item. If the weight limit is 0, can we accommodate it? No. If the weight limit's 1, can we accommodate it? No. The thing has a weight of 5. So not if it's 2, not if it's 3, not if it's 4, but if it is 5, then yeah, we can accommodate it. So we'll say, yeah, we can get a value of 10 from that. We can get a value of 10 from this. We can get a value of 10 from this, and everything beyond that. Okay, cool. And then basically after that, we've got our other thing, and we're going to say now we're including 0 and 1. And we want to go all the way up to maxW. And so we'll say, okay, so can you afford to, can we accommodate weight 2 here as a weight of 4, right? So we'll say, no, we can't until the weight limit becomes 4, at which point we say, oh, great. Well, if our weight limit is 4, then yeah, we could accommodate value 2. And yeah, okay, I'm regretting scratching that out. But anyway, so we would probably have a 6 at that point. Okay. And then after that, if we go on from there and we say, well, now our weight limit would be, let me get more numbers in here, 4, 5, and complete the dot, dot, dot. Okay, so now if the weight limit is 5, well, yeah, we could accommodate our item that has a 6 here, or we could accommodate the other item. So we could say, okay, well, either we'll take this thing, or we won't take it, and instead we'll have, you know, whatever we could take without that thing. So then we would basically have a 10 there because that's bigger. But the main thing is, if we do decide to take this thing, then not only do we get, like, for example, the 6 here, then we say, okay, so we'll now subtract 4 from our weight limit because we've taken an item with a weight of 4. And so now we have 0 left to work with. So what could we get for capacity of 0? Oh, nothing. So then eventually if we get to a point where, you know, we're off over here and maybe our weight limit is, let's see, what would it have to be? Let's say it's 9, right? So then if the weight limit is 9, then, and is that, no, it's not actually part of it, but let's say, no, maybe it's not 8, maybe it's 9 or something else. So if it was 9, then we basically say, okay, can we afford to take item 2? Yeah, we can. It has a weight of 4, so we'll take item 2, which has a value of 6. But then our weight limit, which was 9, we were saying, right? After we take away the 4 from that, so we'll do 9 minus 4, right? So we're taking away the 4 because we're saying, yeah, we are going to take this item. So in terms of our leftover capacity, we're going to say, now it's 5. And so we say, okay, so we'll take the 6, we'll take the value 6 from this one. But then in addition to that, we'll take whatever we were able to get previously for our new capacity of 5. So we say, okay, at a capacity of 9, we're able to take the item of value 6, and then with the leftover capacity, which is 5, we're also able to take the other item, which had a value of 10. So we would actually get a 16 as our total value for that one. Okay, so that's the game plan. I went into a little more detail than I was actually planning on doing, but that's fine. So let's get rid of this for a sec, and let's talk about what we're going to do. So the first thing we notice is we have that row of zeros. So I'm just going to put that in. Let's just say let 0 row be this empty array, and we'll just fill it up for let I is assigned the value of 0, I is less than or equal to, actually, max W. That's very important, I plus plus, and we'll basically just say 0 row dot push 0. They're all zeros on 0 rows. So then after that, we'll say, well, dynamic programming dot push the 0 row. Okay, so then at the end of this, and I'll just return dynamic programming, and we should have just an array of zeros. Actually, sorry, that's my mistake. It's an array containing an array of zeros. How many zeros? Well, it should be the same as max W and then plus an extra 1 because we start at 0 here and we go all the way up to and including max W. So this should have 10, I think. So 5 and 5. Yeah, we're good. Cool. All right, so this is working out nicely. That's our first row, but now we want to get some other rows in there. So we'll say something like for let I be assigned the value of 1, and I is sort of representing the new object that we're bringing in here. So maybe in this case we can imagine I stands for items. Okay, and we're going to keep going until I is less than or I guess less than or equal to values dot length. And I could have just as easily said weights.length. Maybe we could do like a constant called length, but I think this is the only time we need to use it, so maybe that would be overkill. Okay, so what do we want to be doing for each of these things? So as I goes from 0 to values.length, yeah, what do we want to be doing with this? Well, we want to create a new row, first of all, and that row is going to sort of represent like we were saying earlier, and maybe I should have kept that diagram, but oh well. We're basically talking about including all the items up to and including item I. Okay, so this one would include item 1, the next one would include item 2, the next one would include item 3, and as well as all the previous ones. But anyway, at the end of all this, we want to push this row into our dynamic programming array. Okay, so what are we going to be doing with the row here? Well, basically, we need to go from left to right. So we need to do something kind of like, I'll say let limit be assigned the value of 0. Limit needs to go all the way up to the maximum possible limit. And we'll say limit plus plus. So we're basically saying, well, if we can include all these items like up to and including I, then what outcomes do we get? What maximum values do we get for each weight capacity all the way up to and including the maximum weight capacity we're given in the problem? Okay, so the way we're going to deal with this is we'll say let the maximum value be 0, just by default, I guess. Or maybe let's let the maximum value be equal to whatever we had on the previous row. Okay, because we know that for the same capacity on the previous row, so at I minus 1, we were able to get this value, like this was the maximum value we were able to get for this same limit. We're basically just going up a row, and that's fine, because it basically means, okay, well, in that case, we're not taking item I. We're just getting the optimal value we were able to get for all the items before that, for the set of items before that. Okay, and then from there, we'll say, but, if you can accommodate it, so if weights at I minus 1 is less than or equal to the limit, well, then we'll do something with that. Before we go any further, you might be looking at this and saying, I get why you're doing dynamic programming at I minus 1, because we want to be looking at the previous row and not the current one. So like, for example, if I is 1, we want to be looking at row 0, which we have because we did 0 row. But why weights at I minus 1? And the reason is because this I is starting at 1 and weights is an array. So its first element would actually be at 0. So notice how these are 1 based, like 1 and 2, value 1, value 2. Whereas an array is 0 based, so it would be more like, value 0, value 1, that sort of thing. Anyway, so that's why I'm doing the I minus 1 for that. Okay. Now, what are we saying in this case? Well, we're saying weights at I minus 1, so the current weight we're looking at, so whatever the item is, maybe it's 5 is what I was trying to highlight there, or maybe it's 4, like, it depends. But if the limit is big enough that we actually can accommodate this thing, then let's try accommodating this thing. So we'll say max is going to be equal to, and basically the idea is it could be equal to this. It could be equal to values at I minus 1, because we're saying, yeah, if you can accommodate the weight of this thing, get the value of this thing, right? And then in addition to that, how much weight do you have left over? How much weight would we have left over? Well, I'm going to put in one of these first of all, and it's going to be the same as limit minus weights at I minus 1. And maybe I should have used a variable for weights at I minus 1. Oh well. Anyway, the point is, okay, this thing right here represents the remaining capacity, because limit was like our total capacity that we have. Once we do take this item, what's left over is basically what we get after we subtract that weight from our capacity. So what we want to know is, in the previous row, what could that buy you? If you did have this capacity left over, how much would you be able to get from that, according to the previous row, when we weren't including this item? So basically we're saying, if we can take this item, let's try taking this item. So we get the value of that item, plus we get the value of whatever we were able to get without this item for a capacity equal to whatever we would have left over after we actually take this item. So I realize it's getting a bit complicated, and I'm sorry about that, and I'm especially sorry by the fact that it's getting more complicated, because that might not be better, like in this first example. So when we're looking at the two weights, what we found is, you get to a point where you can afford to take the item. So if your limit is 4, then take the item because it's 6. That's better than the 0 you'd get on the previous row for not taking the item. But once it gets to 5, now you say, well, it could be 6 plus 0, or it could just be the 10 that we had on the previous row. So that would be what max already has. That it already has that value. So we need to make sure that this would actually be better than what we already have in there. So we'll do math.max of max, like the value itself, or this new thing that we just found. Okay, cool. Great. So there we go. And then let's see, I guess now we just have to do a row.push max. So we'll put max inside the row. And that should give us the maximum value that we can get for a subset of items up to and including item I for a weight limit of limit. And that goes all the way up to maxW, which is good. But just to get a sense of this thing, to get a sense of what this is all looking like, first of all, let's get rid of that space and let's run the sample tests. We'll see if it's actually working first of all. Okay, it's producing something, so that's pretty neat. And notice when we're including all the items, all 2 of them, so that would be this last array, the last row here. When we're including all the items and when we're looking for a maxW for a limit equal to 8, well, that would take us all the way to this last one over here. Whoops, didn't mean to highlight the whole thing. It would take us to this, the 10. And that's good. That's the value we were looking for in that case. So, maybe that's a coincidence, but the 16 over here is the same as the expected output there. The 7 here is the same as the 7 over there, so that's looking good. Test number 4, 0, 0, 15, 15. It seems like it's pretty consistent. We're not really getting any values that aren't matching there. So if we want to actually get that last value, well, we could say that's going to be dynamic programming at values.length at maxW. And I think that should work. That should give us the value we're looking for. Indeed it does. That's nice. But if you think about it, actually, let's just get a little console log in there. Console.log dynamic programming. Just so we can see like what the whole array looked like in the end. Okay, so yeah, there it is. And we get our value of 10. But if you think about it, like we're looking for the final value in the final array within this matrix. So what we could do is instead of dynamic program at values.length at maxW, we could just say, well, I want to take the last array off of this, right? So we'll do a .pop, and that's basically just going to return this whole array because dynamic programming is a matrix. It's an array of arrays. So we'll return this last array here, but we don't just want that whole last array. We want the last element of that last array. So we're actually going to do .pop, which seems kind of funny. I mean, strange if you haven't seen it before. I actually didn't even really think of doing that until this problem. But yeah, pop, it works. And let's try submitting it. Let's see if we get the right values for all these things. Cool. Okay, so that's nice. But just to sort of, I guess, illustrate a point, let's make another example here. Let's actually change this up. We'll hard code another example here. So we'll say let maxW. Or actually, we don't need a let, it already exists, but we'll say maxW is going to be equal to 25, okay? And we'll do like a bunch of weights. So we'll say we've got an item that has a weight of 10, one that's a weight of 5, one that's a weight of 17, one that's a weight of 3, one that's a weight of, let's say, 24, one that's a weight of 2. Is that good? Let's just do a really expensive one, 48. Okay, cool. Expensive in terms of weight, not necessarily in terms of value. So what are the values going to be? I think I'm just going to make up, random numbers, more or less. So we'll say the first one's worth 20. The second one is worth 15. This one's going to be worth 30. This one's 10. This one's going to be worth 4. That one's worth 9. And this one's worth 1,000. Okay, cool. So for 25, what would be the best outcome here? That's a good question. Okay, well, I think we would want to get that 20 if we can. If we get that 20, it means we can't get the 30, but that's fine because we could get the 20 and the 15 and we'd still have 10 left over. So we could get the 3 and the 2. So that's what, 35 plus 19. So that would be like 54, I think. Anyway, let's try running the test. We'll see if we get any errors or anything like that. We don't, and we get 55. Okay, so maybe I miscalculated here. Or maybe I'm just wrong. So let's see. There's a lot of stuff going on over here. But yeah, it does look like 55 is what we're getting. And we're only getting that, like, if maxW was even one less, then it would be 54 like I calculated. So, okay. Why are we getting that number? That's a good question. I think I probably just added wrong or something like that. I'd have to look into it. Anyway, so point is, this seems to be working. It seems to be working for larger sets of values, you know, not just the ones we were initially looking at, but we actually do want to pass all the tests here, so I'll set it back to what we had. Yeah, perfect. Okay, so now there's just one thing I want to talk about, I guess. So this is so precise. There we go. All right. I just wanted to make this big, mainly because there's a lot to look at here. So let's just get a bit of space in here. And now I have to say, I don't really like this. I don't like the way we have this whole separate loop just for the first row here. So instead of doing that, let's actually start this one at 0. The problem there now is this isn't going to work if there isn't an I-1 in our dynamic programming array, which there wouldn't be if we deleted all that stuff. Okay, so then basically for this part here, we know that the row is going to get the value of max pushed in, right? So since it's going to become max, let's do this. We'll say let max be assigned the value of 0. So by default, it's 0. And if I is greater than 0, so if we're not talking about the first one, well then we'll do this other stuff, and you know we'll change up the value of max here. We don't need a let. In fact, it would be bad to have the let in there. And we'll move that over. We'll clean this up a little bit, and let's see if that maybe works. We'll see if it still works, first of all. And there we go. No. Okay. 0 row is not defined. Sure isn't. Let's get rid of that. And we'll run the tests. Hopefully that works. Yeah, that's working. I like that better. So, okay. Let's clean this up a little bit and we'll throw in a little comment. So, dynamic programming algorithm works for any number of elements. Nice. Okay, great. So that's good. I feel good about that one. I like the pop at the end there. I'm going to keep the console log just so that we can sort of see what the whole thing looks like. I mean, it might shed some light on the whole thing. Let's see. Maybe I'll make a comment here and say something like, for dynamic programming array, each row represents a subset of elements up to and including item I, we'll say. And then each column represents a weight limit of, we'll call it J, and then up to maxW. Great. So that's basically what our dynamic programming array is doing. So yeah, let me know if you have any questions, comments, or concerns on this one. I'll submit it now that it has all those nice comments in it. Great, so that's passing. Is there anything left to say about this one? I'm thinking no. So, nice job. We did it. Congrats. All right, we'll move on.